We have already discussed how to verify your goodness of fit using R-square goodness of fit and how to make inference on model parameters. So the importance of individual variables in explaining your dependent variable. However, a full study of a regression model covers also possible outlier identification as well as the analysis of residuals. So that's another way to verify the overall goodness of fit. Now let's start from outliers. So now when we have our regression fit and we make the difference between the fit and the original data, and then we rescale that residual series by its standard deviation, then we get t-statistic for those error terms. And again, as a rule of thumb, any t-statistic standing out beyond values of -3 and 3 can be suspected to be an outlier, because it means it's statistically unlikely among this set of observations. Now, what could cause outliers? Well, if you have some electronic device measuring a phenomenon, then that device may malfunction and it will give some crazy reading just because something has happened. Maybe there are some specific conditions when it has caused how the device works. Another way would be somebody's writing down results on paper and then copying them to the computer and makes a mistake and reads some digit incorrectly, or another person reading other person's handwriting makes a mistake, or just a simple typo. So we have to be aware that those things happen, but also we have to be aware that there are phenomena where outlying values are actually normal. So whenever you're studying something, you should be aware, could it be considered a normal observation or not? Now, how can outliers mess up our work? Well, if you think of it, that you have some nice looking data and you can really fit in there either a nice looking straight line or a polynomial, and then there is this one observation which sticks out. So remember that this is far away and it is pulling this regression fit line away from the rest of the data. So it could mean that your regression fit with this outlier would actually look like that. So it wouldn't be halfway there, because remember that the model is fitted using least squares, so we're actually penalizing things which are far away more than those which are close nearby. But still, that could distort your model quite significantly. So what should we do about outliers? Well, you could either remove them, so just get rid of that one observation, or if you have small data set and you really need all your data points, you may replace that outlier with a mean value of your data set, but also that is not always appropriate. You may need to replace it maybe by the average of the two neighboring observations. So that again really depends on the phenomena you're modeling and on the fact how much that outlier should actually be considered an outlier and how much can actually be allowed to be part of the data set. And then another part of verifying your regression fit is checking the residuals. So now, once you have your residual series, it should roughly look like a series of random numbers. So it shouldn't have any serial correlation in it. But if you do see some patterns, like for instance quadratic-like looking residual series, like here, or if you see a funnel shape like that, so maybe the variance of the residuals is higher on one side and lower on the other one. So that may mean that your model may be missing some critical transformation. So this kind of quadratic look in the residuals may indicate that you want to add quadratic terms or transform your data before you even do the fit. And then if you have this kind of funnel shape, whichever way, that may mean that your data may need logarithmic transformation. And finally, for the overall model of fit, we already discussed the R-square. So we would be measuring how much better the distances between our data and the linear fit are smaller than the distances between the data and the overall mean of the data. So if we calculate those different sums of squares, so we have the total sum of squares, which is the differences, as we said, between the data and the mean value of the data, and then we would have sum of squares between the model fit and the mean value of the data. And finally, we have the sums of squares of the errors, so the residuals, which is between our original data and the fit. So the points, how far they are away from our straight line. So if we think of testing, we can measure exactly how far our fit is away from the mean value, and then how far the data points are away from the fit. And it turns out that if that variability, so if our fit is away from the mean value much more than our original data points are away from our fit line, then it means that those residuals, the errors of our fit, are small enough for us to judge that the model is significant. So this ratio, if this F-statistic is high, we have the acceptance rejection region. So null hypothesis in here that all the parameters, actually what is missing here, is equal to 0. So it means that if F-statistic is low, it means that we assume all the parameters are not significantly different from 0, so that the model is not significant in overall. But if, once again, our variations, so the distance, how far our model errors are away from the fit line, when compared to how far our line, so the fit, is away from the mean value, so this ratio, when it's high, means that our fit is good. And then in here, this 2 in here stands for number of parameters in the model. So this is for the one variable straight line, but it will be k or p if we talk about p explanatory variables, or p plus 1 if there is also an intercept in the model. So basically, in the place of 2 in this case, we should actually have the number of model parameters, so it may be more than 2. And then similarly as before, as with any other testing, for our F-statistic, we can actually calculate the p-value. So based on that p-value, we would know what is the reliability of our model. So high F value equivalent to small p-value is equivalent to being able to say, or having strong evidence, that at least one of the model parameters in here is significantly different from 0. You may notice similarity to ANOVA testing, where we were testing equality of different mean values. Now we are testing also for equality and equality to 0, whereas the alternative is that at least one of these is significantly different from 0, which means that at least one of the variables we've included in our model provides enough input to make the overall regression fit reliable. And then to know which one that is, then of course we go into inference on the model parameters, which we have already discussed. And one more important thing to be mentioned here is that our residuals need to be normally distributed in order to be able to make statistical inference on F-test. Because remember that only a sum of squared normal distributions creates a chi-square distribution, and division of two chi-square distributions creates an F distribution. So in order to make this inference, at the point where we are studying model residuals, we should actually test them for normality. And only when that test is accepted, it means that the residuals are appropriate, so we can conclude on the final goodness of fit of the model.